Membrane filtration. A membrane is a thin layer of semi-permeable material that separates substances when a driving force is applied across the membrane. Membrane processes are increasingly used for removal of bacteria, microorganisms, particulates, and natural organic material, which can impart color, tastes, and odors to water and react with disinfectants to form disinfection byproducts. As advancements are made in membrane production and module design, capital and operating costs continue to decline. The membrane processes discussed here are microfiltration, MF, ultrafiltration, UF, nanofiltration, NF, and reverse osmosis, RO. Microfiltration. Microfiltration is loosely defined as a membrane separation process using membranes with a pore size of approximately 0.03 to 10 micronas. 1 micron equals 0.001 millimeter. A molecular weight cutoff, MWCO, of greater than 1 million Daltons and a relatively low feed water operating pressure of approximately 100 to 400 kPa, 15 to 60 psi. Materials removed by microfiltration include sand, silt, clays, giardia lamblia, and cryptosporidium cysts, algae, and some bacterial species. Microfiltration is not an absolute barrier to viruses. However, when used in combination with disinfection, microfiltration appears to control these microorganisms in water. There is a growing emphasis on limiting the concentrations, and number of chemicals that are applied during water treatment. By physically removing the pathogens, membrane filtration can significantly reduce chemical addition, such as chlorination. Another application for the technology is for removal of natural synthetic organic matter to reduce fouling potential. In its normal operation, microfiltration removes little or no organic matter. However, when pretreatment is applied, increased removal of organic material can occur. Microfiltration can be used as a pretreatment to reverse osmosis or nanofiltration to reduce fouling potential. Both reverse osmosis and nanofiltration have been traditionally employed to desalt or remove hardness from groundwater. Ultrafiltration. Ultrafiltration has a pore size of approximately 0.002 to 0.1 microns, an MWCO of approximately 10,000 to 100,000 Daltons, and an operating pressure of approximately 200 to 700 kPa, 30 to 100 psi. Ultrafiltration will remove all microbiological species removed by microfiltration, as well as some viruses and humic materials. Disinfection can provide a second barrier to contamination and is therefore recommended. Ultrafiltration has a pore size of approximately 0.002 to 0.1 microns, an MWCO of approximately 10,000 to 100,000 Daltons, and an operating pressure of approximately 200 to 700 kPa, 30 to 100 psi. Ultrafiltration will remove all microbiological species removed by microfiltration, partial removal of bacteria, as well as some viruses, but not an absolute barrier to viruses, and humic materials. Disinfection can provide a second barrier to contamination and is therefore recommended. The primary advantages of low pressure ultrafiltration membrane processes are compared with conventional clarification and disinfection. Post-chlorination processes are no need for chemicals, coagulants, flocculants, disinfectants, pH adjustment, size exclusion filtration as opposed to media depth filtration. Constant quality of the treated water in terms of particle and microbial removal. Process and plant compactness. Simple automation. However, fouling can cause difficulties in membrane technology for water treatment. Nanofiltration. Nanofiltration membranes have a nominal pore size of approximately 0.001 microns and an MWCO of 1,000 to 100,000 Daltons. Pushing water through these smaller membrane pores requires a higher operation pressure than either microfiltration or ultrafiltration. Operating pressures are usually near 600 kPa, 90 psi, and can be as high as 1,000 kPa, 150 psi. These systems can remove virtually all cysts, bacteria, viruses, and humic materials. They provide excellent protection from DBP formation if the disinfectant residual is added after the membrane filtration step. Because nanofiltration membranes also remove alkalinity, the product water can be corrosive, and measures such as blending raw water and product water or adding alkalinity may be needed to reduce corrosivity. Nanofiltration also removes hardness from water, which accounts for nanofiltration membranes sometimes being called softening membranes. Hard water treated by nanofiltration will need pretreatment to avoid precipitation of hardness ions on the membrane. However, more energy is required for nanofiltration than microfiltration or ultrafiltration. Reverse osmosis. Reverse osmosis can effectively remove nearly all inorganic contaminants from water. Reverse osmosis can also effectively remove radium, natural organic substances, pesticides, cysts, bacteria, and viruses. Reverse osmosis is particularly effective when used in series with multiple units. Disinfection is also recommended to ensure the safety of water. Some of the advantages of reverse osmosis are: removes nearly all contaminant ions and most dissolved non-ions. Relatively insensitive to flow and total dissolved solids. TDS level and suitable for small systems with a high degree of seasonal fluctuation in water demand. Reverse osmosis operates immediately without any minimum break-in period. Low effluent concentration possible. Bacteria and particles are also removed, and operational simplicity and automation allow for less operator attention and make reverse osmosis suitable for small systems applications. Some of the limitations of reverse osmosis are: high capital and operating costs, managing the wastewater brine solution is a potential problem. High level of pretreatment is required in some cases. Membranes are prone to fouling and produces the most wastewater at between 25 to 50% of the feed. See figure 13.3. Membrane materials. Normally, membrane material is manufactured from a synthetic polymer, although other forms, including ceramic and metallic membranes, may be available. Almost all membranes manufactured for drinking water are made of polymeric material, since they are significantly less expensive than membranes constructed of other materials. Membranes constructed of polymers that react with oxidants used in drinking water treatment should not be used with chlorinated feed water. Mechanical strength is another consideration, since a membrane with greater strength can withstand larger transmembrane pressure, TMP, levels, allowing for greater operational flexibility and the use of higher pressures. Membranes with bidirectional strength may allow cleaning operations or integrity testing to be performed from either feed or filtrate side of the membrane. Membranes with a particular surface charge may remove particulate or microbial contaminants of the opposite charge due to the electrostatic attraction. Membranes can also be hydrophilic, water attracting, or hydrophobic, water repelling. These terms describe how easily membranes can be wetted, as well as its ability to resist fouling to some degree. Microfiltration and ultrafiltration membranes may be constructed from a wide variety of materials, including cellulose acetate, polyvinylidene fluoride, polyacrylonitrile, polypropylene, polysulfone, polyethersulfone, or other polymers. Each of these materials has different properties with respect to the surface charge, degree of hydrophobicity, pH, and oxidant tolerance, strength, and flexibility. Nanofiltration and reverse osmosis membranes are generally manufactured from cellulose acetate or polyamide materials, and their various advantages and disadvantages. Cellulose membranes are susceptible to biodegradation and must be operated within a narrow pH range of 4 to 8, but they do have some resistance to continuous low-level oxidants. Chlorine doses of 0.5 milligrams per liter or less may control biodegradation and biological fouling without damage to the membrane. Polyamide membranes, by contrast, can be used under a wide range of pH conditions and are not subject to biodegradation. Although these membranes have very limited tolerance for strong oxidants, they are compatible with weaker oxidants such as chloramines. These membranes require significantly less pressure to operate and have become the predominant material used for nanofiltration or reverse osmosis applications. Membrane modules. Membrane filters are usually manufactured as flat sheet stock or as hollow fibers and then formed into and of several different types of membrane modules. Module construction typically involves potting or sealing the membrane material into an assembly, such as with hollow fiber modules. These types of modules are designed for long-term use over the course of a number of years. Spiral wound modules are also manufactured for long-term use, although these modules are encased in a separate pressure vessel that is independent of the module itself. Hollow fiber modules. Most hollow fiber modules used in drinking water treatment applications are manufactured for microfiltration or ultrafiltration membranes to filter particulate matter. These modules are comprised of hollow fiber membranes, which are long and very narrow tubes that may be constructed of membrane materials described previously. The fibers may be bundled in one of several different arrangements. Fibers can be bundled together longitudinally, potted in a resin on both ends, and encased in a pressure vessel. These modules are typically mounted vertically, although horizontal mounting may be used. These fibers can be similar to spiral wound modules and inserted into pressure vessels independent of the module itself. These modules and the pressure vessels are mounted horizontally. Bundled hollow fibers can also be vertically and submerged in a basin that does not need a pressure vessel. A typical hollow fiber module may consist of several hundred to over 10,000 fibers. Although dimensions vary by manufacturer, approximate ranges for hollow fiber constructions are: outside diameter 0.5 to 2 micrometers, millimeters. Inside diameter 0.3 to 1 mm. Fiber wall thickness 0.1 to 0.6 mm. Fiber length 1 to 2 meters. Outside diameter 0.5 to 2.0 millimeters. Inside diameter 0.3 to 1.0 millimeters. Fiber wall thickness 0.1 to 0.6 millimeters. Fiber length 1 to 2 meters. Hollow fiber membrane modules may operate in an inside-out or outside-in mode. In inside-out mode, feed water enters the center of the fiber lumen and is filtered radially through the fiber wall. Filtrate is then collected from outside the fiber. During outside-in operation, feed water passes from outside the fiber to the inside, where filtrate is collected in the center of the fiber. See figure. Hollow fiber cross-section photomicrograph. When a hollow fiber module is operated in an inside-out mode, Pressurized feed water may enter the center of the fiber at either end of the module, while filtrate exits through a port located at the center or end of the module. In outside in mode, feed water typically enters the module through an inlet port located in the center and is filtered into the center of the fiber, where the filtrate exits through a port at one end of the module. Most hollow fiber systems operate in direct filtration mode and are periodically backwashed to remove the accumulated solids. Spiral wound modules. Spiral wound modules were developed to remove dissolved solids and are most often associated with NF-RO processes, nanofiltration, reverse osmosis processes. The basic unit is a sandwich of flat membrane sheets called a leaf, wound around a central perforated tube. One leaf consists of two membrane sheets placed back to back and separated by a spacer called permeate carrier. Layers of the leaf are glued along three edges, while the unglued edge is sealed around the perforated central tube. Feed water enters the spacer channels at the end of the spiral wound element in a path parallel to the central tube. A feed water flows through the spacers. A portion permeates through either of the two surrounding membrane layers and into the permeate carrier, leaving behind any dissolved and particulate contaminants that are rejected by the membrane. Filtered water in the permeate carrier travels spirally inward toward the central collector tube, while water in the feed spacer that does not permeate through the membrane continues to flow across the membrane surface, becoming increasingly concentrated with rejected contaminants. This concentrate stream exits the element parallel to the central tube through the opposite end from which the feed water entered. See inside out and outside in modes of operation using pressure vessels. Figure. See spiral wound membrane module figure. Deposition mode. Deposition mode. Membrane filtration systems operating in deposition have one influent, feed, and one effluent, filtrate stream. These systems are also commonly called dead end or direct filtration systems and are similar to conventional granular media filters in terms of hydraulic configuration. In deposition mode, contaminants suspended in the feed stream accumulate on the membrane surface and are held in place by hydraulic forces acting perpendicular to the membrane, forming a cake layer. See schematic of a system operating in deposition mode. Figure. C. Deposition mode. Figure. Feed, cake layer, membrane, filtrate. Most hollow fiber microfiltration and ultrafiltration systems operate in deposition mode. Typically, accumulated solids are removed from microfiltration ultrafiltration systems, MFUF systems, by backwashing. However, some systems operate until accumulated solids reduce the flow and or TMP to an unacceptable level, at which point the membrane cartridge is replaced. Some MFUF systems utilize a periodic backpulse or a short interval of reverse flow, which may include air and or addition of small doses of oxidants designed to dislodge particles from the membrane surface without removing these solids from the system. This process resuspends particles, effectively concentrating the suspended solids in the feed near the membrane surface and increasing the potential for pathogens or other particulates to pass through an integrity breach and contaminate the filtrate. Suspension mode. In membrane filtration systems that operate in suspension mode, a scurrying force using water and or air is applied parallel to the membrane during production of the filtrate in a continuous or intermittent manner. The objective of operating in this mode is to minimize the accumulation of contaminants at the membrane surface or boundary layer, thus reducing fouling. See suspension mode figure. Feed, concentrate, boundary layer, membrane, filtrate. Backwashing. The backwashing process is designed to remove contaminants accumulated on the membrane. Each membrane unit is backwashed separately and in a staggered pattern to minimize the number of units in simultaneous backwash at any given time. During backwash, the direction of flow is reversed for 30 seconds to 3 minutes. The force and direction of the flow dislodge the contaminants at the membrane surface and wash accumulated solids out through the discharge line. Membrane filtration systems are 15 to 60 minutes between backwash events. The backwash process reduces system productivity 5 to 10% due to the volume of filtrate used during backwash. Backwashing is almost exclusively associated with hollow fiber microfiltration and ultrafiltration processes. Backwashing is conducted according to manufacturer specifications and site-specific considerations. Although more frequent backwashing allows for higher fluxes, this is counterbalanced by the decrease in system productivity. In general, A backwash cycle is triggered with a performance-based benchmark is exceeded, such as operating time, volume, increase in TMP, and or flux decline. Ideally, the backwash process restores the TMP to its clean level. However, most membranes exhibit a gradual increase in TMP after each backwash, indicating accumulations of foulants that cannot be removed by the backwash process alone. These foulants and are addressed through chemical cleaning. Some systems also utilize pressurized air and or chlorine in combination with filtered water to remove solids, provide pathogen inactivation and biofouling control, and improve backwash effectiveness. A disinfectant such as chlorine may be added at every backwash to once per day. Some MF-UF membranes use chemicals other than chlorine, such as acids, bases, surfactants, or other proprietary chemicals. These strategies are used to enhance membrane flux and extend intervals between chemical cleanings, thus lowering the cost of operation. State regulators may require enhanced cross-connection control measures for backwash piping and special provisions for rinsing the membranes after backwash be required. Because spiral wound membranes generally do not permit reverse flow, nanofiltration and reverse osmosis membrane systems are not backwashed. For these systems, membrane fouling is controlled with chemical cleaning, flux control, and cross-flow velocity. The inability of spiral wound membranes to be backwashed is one reason nanofiltration and reverse osmosis membranes are seldom applied to directly treat water with high turbidity or suspended solids. Chemical cleaning. Chemical cleaning also controls membrane fouling, particularly inorganic scaling and organic and befouling that is not removed with backwash. Chemical cleaning is conducted for each membrane unit separately and is typically staggered to minimize the number of units undergoing cleaning at any time. While chemical cleaning is conducted on both MFUF and NFRO systems, chemical cleaning is the primary means of removing foulants in NFRO systems. Although cleaning intervals may vary on a system-by-system basis, gradual accumulation of foulants make chemical cleaning necessary. Membrane cartridge filters are an exception. However, in that cartridge filters are usually designed to be disposable and are not subject to chemical cleaning. The goal of chemical cleaning is to restore the TMP of the system to its clean level. Any foulant that is removed by either the backwash or chemical cleaning process is known as reversible fouling. Over time, membrane processes also experience some degree of irreversible fouling, which cannot be removed through chemical cleaning or backwashing. Irreversible fouling occurs in all membrane systems and eventually requires membrane replacement. There are a variety of different chemicals that may be used for membrane cleaning, and each is targeted to remove a specific form of fouling. For example, citric acid is used to dissolve inorganic scaling. Strong bases such as caustic are typically used to dissolve organic material. Detergents and surfactants may also be used to remove organic and particulate foulants, particularly those that are difficult to dissolve. Chemical cleaning may also use a strong chlorine solution to control biofouling. Due to the variety of foulants present in source waters, it is often necessary to use a combination of different chemicals in series to address multiple types of fouling. See chemical agents, chemical cleaning agents table. Category: chemicals commonly used. Typical target contaminant. Acids. Acid for citric acid, C6H8O7. Hydrochloric acid, HCl. Typical target contaminants. Inorganic scale. Inorganic scale. Category: base, caustic, NaOH, used for organics. Category: oxidants or disinfectants. Sodium hypochlorite, NaOCl. Chlorine gas, Cl2. Hydrogen peroxide, H2O. For organics, biofilms. Category: surfactants. Chemicals commonly used, varies. Typical target contaminants, organics or inert particles. Proprietary cleaning chemicals are available, and these specialty cleaning agents may be useful when more conventional chemicals are ineffective. For example, enzymatic cleaners have been effective at dissolving organic contaminants. Chemical cleaning options are limited for membranes that cannot tolerate oxidants and or extreme pH levels. A chemical cleaning regimen may be specified by the manufacturer based on site-specific source water quality. Clean in place, CIP, is often used to describe chemical cleaning since it is typically conducted while the membrane modules remain within the membrane unit in situ. The cleaning process recirculates a cleaning solution through the membrane system at high velocities to generate scurrying action and elevated temperature to enhance the solubility of the foulants. A soak cycle follows the recirculation phase. After the soak cycle, the membrane system is flushed to remove residual traces of the cleaning solutions. The processes may be repeated using a different cleaning solution to target different types of foulants until the membranes have been successfully cleaned. Softened or demineralized water may be required for the cleaning solution or as rinse water. While backwashing may be conducted at more regular intervals, chemical cleaning is done only when necessary. Chemical cleaning is generally necessary for MF and UF systems when periodic backwashing to restore system productivity reaches a point of diminishing returns. For NF and RO systems, a 10 to 15% decline in flux or a 50% increase in differential pressure may indicate the need for chemical cleaning. Delaying necessary chemical cleaning can accelerate irreversible fouling, reduce production capacity, and shorten membrane life. A benchmark of 30 days is commonly used as a minimum required interval between chemical cleanings for MFUF systems. Although a well-designed system may operate for much longer between cleanings, NFRO systems are normally designed to operate for much longer periods between chemical cleanings, from 3 months to 1 year. In addition to a CIP, clean in place, when a point of diminishing productivity is reached, some MF/UF membrane system manufacturers recommend a routine, short duration chemical cleaning to minimize the accumulation of foulants. These processes are referred to chemical washes or maintenance cleans and are implemented on preset intervals ranging from several times per day to once every several days, depending on the propensity of the water to cause membrane fouling. Isolating cleaning chemicals from the treated, filtered water is an important consideration. In addition, it is important to properly flush the membrane unit after the cleaning process and before restarting the filtration cycle. The flushed water should be diverted to waste until filtrate water quality parameters, turbidity for MFUF systems, and pH for NFRO systems return to normal levels. The volume of flushed water can be significant when surfactants are used. For MFUS systems, it is common to recycle as much as 90% of the cleaning chemicals for reuse, thus reducing the volume of chemical waste as well as the cost associated with cleaning. Recycling cleaning solutions is less common with NFRO systems, since used cleaning solutions accumulate dissolved constituents with repeated use, diminishing effectiveness of the cleaning agents. Waste stream disposal. Waste stream disposal is a significant problem in many areas. Unlike conventional treatment processes, in which approximately 50 to 10% of the influent water is discharged as waste, membrane processes produce waste streams as much as 15% of the total treated water volume. Because little or no chemical treatment is used in a membrane system, the concentrate stream usually contains only the contaminants found in source water, although at much higher concentrations. And concentrate can sometimes be disposed of in the source water. Other alternatives include deep well injection, dilution and spray irrigation, or disposal in municipal sewer. These alternatives are usually necessary for nanofiltration wastes, which usually contain concentrated organic and inorganic compounds. Disposal must be carefully considered, and applicable discharge regulations must be respected. Membrane integrity testing. One of the most critical aspects of employing membrane technology is ensuring that the membranes are intact and continuing to provide a barrier between the feed water and the permanent or product water. There are several different methods that can be employed to monitor membrane integrity, including turbidity monitoring, particle counting or monitoring, air pressure testing, bubble point testing, sonic wave sensing, and biological monitoring. Adapted from PA, Pennsylvania website, dated November 2005, and National Drinking Water Clearinghouse website, dated March 1999. Membrane filtration.